Okay, I think we can start. Good morning, everyone, or good day. Depends where you are watching us. We are starting the Friday morning session of the 4th Zildovich meeting, which is discussing exoplanets and astrobiology. We are, of course, traditionally interested in these topics since the very first meeting, where several important talks were given back in 2008. However, since then, things changed a lot. As you know, last year there was a Nobel Prize given to the important work in this field. And there is, of course, a strong connection between the astrophysics and cosmology topics and this particular topic, because, of course, we are living on the rocky planet with the atmosphere, and all the chemical elements are built in the universe around us during the formation of stars, explosion of stars, and these are all the topics of interest in astrophysics and cosmology. Besides that, we have discovered also during this meeting that interesting possibilities exist for another astrophysically specially designed missions. In particular, Joyce Hill yesterday was talking about the telescopes to be put hopefully on the moon, which would facilitate observation of exoplanets. I think Stefan Gillison also mentioned observation of exoplanets, and Lorenzo Amati as well in the Monday session. Therefore, we see also practical ways to bridge these fields. And I'm very happy that today we have three distinguished speakers, Ignas Snellen, Amaury Triaud, and Artem Burdanov, who agreed to join us for this meeting. Therefore, let me invite Ignas first to speak on exoplanets and the search for extraterrestrial life. Please, you can start.
Thank you. Can you actually hear me? Thank you. Hello, everybody. Very nice that you are listening in. Thank you for having me. It is a great honor. So my talk is on exoplanets and the search for life. So when you work in this field for a while, you sometimes forget that only 3 decades ago, the only planets that we knew were those in our own solar system. Yeah, and then everything changed. 51 Pegasus B was found, now awarded with the Nobel Prize. I think something that the field can be very, very proud of. And that was the onset of a real revolution. A few years later, the first transit was measured, the first atmosphere, then thermal emission, also moving away from hot Jupiters. Exo-Neptunes were found, the first direct image, molecules, atmospheric winds, planet spin. And in the meantime, finding thousands of planets down to the first exo-Earth, planets with masses and sizes like Earth, which could also have similar climates, and also liquid water on their surface. Of course, I mean here Proxima b and the TRAPPIST-1 planets. Now, this revolution is here because our instruments are getting much better. For example, the accuracy of radial velocity measurements has since the 1980s increased by a factor of 1,000 or so. In this way, we can also peer in the future. You know, great new observatories are coming online, the James Webb and the ELTs, which is very exciting. And yeah, we can start probing the atmospheres of mini Neptune, super Earths, and even some Earth-like planets around nearby M-dwarfs, possibly even probing biomarker gases. Now, in this talk, I will broadly show where we are now and how we want to start doing this. Okay, maybe it's good to first discuss briefly why we are actually all doing this. I often have to explain this in public talks. I get comments like, who cares about other Earths many light years away? We can never go there anyway, and such. Well, this is not about distant world per se. This quest is really about ourselves. You know, what are we doing here? About understanding the place and role of the Earth and the solar system in the universe as a whole. So this has a very strong philosophical aspect. You know, we can ask existential questions about humanity and life on Earth. Now, how do planets form? How does the solar system fit in? Is it in any way special? And if so, why is it special? And then, the 100 billion euro question, are we actually alone? Does life exist elsewhere? I think this can really change the way we see ourselves. You know, like Galilei's work did 500 years ago, like Darwin did, and also, for example, the first Apollo photos of the Earth as a whole. Now, I think that evidence for extraterrestrial life will really sharpen the view of ourselves further. Okay, before we go to the exoplanets, there are, of course, planets that we know very well, those in our own solar system. What do we, very broadly speaking, learn from them? Well, clearly planets are very complex and diverse systems, much more than, for example, stars, which you can mostly describe using only a few parameters. This is not the case for planets. You know, you only have to look at the rocky planets and moons with an atmosphere, Venus, Earth, Mars, and Titan. They are so different. Venus has a very thick sulfuric acid clouds in a CO2-based atmosphere. Earth is nitrogen-based. It's partially clear with water clouds and a large fraction of oxygen, of course. And then the atmosphere is very thin. It's CO2-based again. And Titan has a thick nitrogen-based atmosphere with opaque methane, ethane clouds. I would say, how are we ever going to make any sense out of this mess? Well, I like to compare that with one of my all-time heroes. I already mentioned him briefly, Charles Darwin. What if Darwin only knew about 3 species, an owl, a monkey, and a scorpion? Of course, he would never be able to come up with his great theory about the tree of life. You know, he goes on this epic journey aboard the Beagle, along the shores and coasts of distant islands, just to see what is actually out there. And I see our exoplanet endeavor also a bit as an epic journey in that way. It's going to be really hard and really difficult. But I think it's going to be the only way to begin to see possible families, orders of classes of planets and understand their formation and evolutionary relationships. So where are we now? No, after 25 years of exoplanet research, we found more than 4,000 planets, and the diversity we see is even larger than in our own solar system. You know, all these type of planets which we did not know could actually exist, like hot Jupiters, gas giant planets in very short orbits, not clear to us how they are actually formed. You have these super Jupiters at very large orbital distances, up to hundreds of AU. How do they actually get out there? And then there's, for example, this very diverse class of mini Neptunes and super Earths, very common in the Milky Way, but not in our own solar system, again. Now, we now know that about 1 in 10 stars host a Jupiter mass planet, about 1 in 5 stars in Neptune, and most stars have Earth mass planets. So these are really common. And this has, of course, now resulted in a very important recent milestone, as we all know, the actual discovery of Proxima b, an Earth mass planet around our nearest neighbor. Now, although Proxima b is only in an 11-day orbit, actually Proxima itself is so weak compared to the Sun that the planet receives starlight at the same level a planet would have in an orbit somewhere between the Earth and Mars. So it could actually well have liquid water on its surface. Another very fascinating system is, of course, TRAPPIST-1, with 7 sister Earth planets, of which 3 or more could have such a climate that liquid water could actually exist on their surfaces. I think this is really, really exciting. Okay, when we characterize planets, what are actually the global properties we would like to find out? what questions can we actually ask ourselves? Well, first of all, very general, what is the bulk composition of a planet? Then does it have an atmosphere or not? What is its chemical makeup? What is its climate like? How hot or how warm, and what differences between the day and night side? And can we link any of these properties with the formation and evolution of the exoplanet? And do we really then understand all the physical and chemical processes? Also possibly linked to any geological processes of the planet. Now, homing in on Earth-like planets, we can ask to what extent the planet has water, has possibly any biosignature gases such as oxygen, ozone, or methane. And then probably the most difficult question of all, are these biomarker gases really due to biological activity or not? Now, of course, for molecular oxygen and ozone on Earth, this is actually the case, but theorists have already identified several other processes on rocky planet atmospheres that could also lead to oxygen buildup. For example, by the evaporation of a significant ocean, when the hydrogen atoms for water ultimately escape to space, leaving the actual oxygen atoms behind. Now, luckily, we think the same models show that these different scenarios can be identified by the presence or not of other molecules, such as CO, CO2, or methane. All right, and then, we want to observe an atmosphere. Although we now know of thousands of planets, you should realize that almost all of them have been found without identifying a single photon from the planets themselves. When you want to do atmospheric measurements, you no longer can actually do that. You need to separate out the planet light from that of the stars. Well, there are basically two families of methods to actually do this. One are the time differential methods. The appearance of the planet changes as a function of time in the case of transits, eclipses, and phase curves. And the second are angular differential methods, and that is spatially separating the planet lights from that of the star. This is basically direct imaging. Now, both these methods, they work the easiest for warm planets. For transits, these are the hot Jupiters and short orbits. And for direct imaging, these are very young gas giants, far away from the host star, which are still hot from their formation. Now, both methods have already been very successful with many measurements of different molecules, atoms, ions, temperature pressure profiles from day to night side, evidence for exospheric loss, for example, Rayleigh scattering from hazes, evidence for cloud. Of course, the mean particle density of an atmosphere can be measured through the atmospheric scale height, global circulation patterns, even direct measurements of winds and planet spin. Now, like all of us, we are eagerly awaiting the launch of the James Webb, which will be particularly powerful for these time differential measurements. So the transit, eclipses, and phase curves. I think it will move the field really firmly forward, away from hot Jupiters to cooler and smaller planets, Neptunes and super Earth. And this is what I really like about our field. Now, with James Webb, we can also start to find out whether the TRAPPIST planets have an atmosphere and whether it is CO2 based or not. Now, this is only 5 or 6 years after the actual discovery of the system. We can already think about measuring such properties. I think this is extremely exciting. On the left, you can see models of the brightness temperature as a function of wavelength in the mirroring regime. Different levels of atmospheric mass will actually result in different levels of day to night side heat circulation, which you can measure with only a few eclipses. And then also by comparing the brightness at 12 and 15 micron, one can actually identify CO2 absorption or not. It's really exciting. And there are observations that already will be done very early on as part of the MIRI guaranteed time observations. Now, on the right here, one can already see a glimpse of what is possible now. These are observations from Spitzer, led by Laura Kreitberg, who is now Max Planck director in Heidelberg. The planet is only in an 11-hour orbit around the nearby late M dwarf, and it's very hot on its day side, but so cold on its night side that it's actually very unlikely that it has an atmosphere at all, as is expected from models. Now, the James Webb will be orders of magnitude better, and so the Amaury team will do this for the TRAPPIST planets, which are significantly cooler. We will find out to what extent they will actually have an atmosphere or not. Now, in the case of ground-based observations, these families of measurements are combined very well with spectroscopic information. The fact that the planets have different spectral features than the star, either due to Doppler shifts or just other molecular features, helps to separate out the planet light from the star and also from possible Earth atmospheric interference. Now, these are methods that we have developed and refined over the last decade in my group in Leiden, and use high dispersion spectroscopy at the resolution of 100,000, probing the tens or hundreds of individual lines of a molecular band. Now, due to strong Doppler effects, due to the orbital motion of the planet, for the Earth this is 30 kilometers per second around the Sun, but for hot Jupiters it can actually be up to 150 kilometers per second or more. That means that you get these Doppler effects, measurable Doppler effects, even during only a few hours of observation. The planet lines now move through the spectrum, allowing one to separate them out from the non-moving telluric and stellar lines that can actually be orders of magnitude stronger. Now, on this slide, you can see some of the earlier results on CO, both in transmission and emission. But regarding the time, I want to jump to some really exciting recent results from other groups, which I briefly like to show here. On the left, in orange, you can see measurements led by the Amsterdam group using the HARPS North spectrograph on the TNG. This is probing the dayside emission of Kelt 9. This is an amazingly hot planet, at 4,000 Kelvin. It's actually hotter than most of the stars in the Milky Way. And you can see in the top left panel, if you squeeze your eyes a bit, a curved trail of emission. The middle panel actually shows a model of it. This planet is so hot that it's actually glowing in iron. It's quite amazing. Definitely not a planet you want to visit. And then on the right side, you see results from a recent Nature paper led by the Geneva group using the new espresso spectrograph on the VLT. And these are observations made during a transit, again, of iron, but of the hot Jupiter WASP 76b. Yellow here is the iron absorption, with on the vertical axis time, and on the horizontal axis the velocity at which the iron is seen relative to the planet rest frame. And so at the beginning of the transit, on the bottom, you see a little bit of blue shift, which increases up to 15 kilometers per second or so. It's 50,000 kilometers per hour. It's quite a wind. And they have actually a very nice idea of what they are seeing here. During the transit, the orientation of the planet swings back and forth a little bit, meaning that at different times during the transit, we see actually different parts of the morning and evening regions of the planet. Now, they actually show that these observations are explained by there being no iron in the region just before sunrise, meaning actually that the iron rains out on the night side. I think it's quite amazing that we can actually start to find out what the weather is like on worlds several hundred light years away. Now, one reason why this method works so well from the ground is that it makes use of a double differential methods, differential in time and differential in wavelength. But this also really makes this a game of photons. We need more photons. We need a bigger telescope. This is why we get so excited by the ELTs. METIS is a first light instrument with a resolution of 100,000. It will have an integral field unit between 3 and 5 micron. And high-res will be a second-generation spectrograph in the optical and near-infrared, also at very high spectral resolution. Now, both can really do mouth-watering things. For transit observations, the larger telescope directly translates in a significant increase in signal to noise. An example here in green on the left, we can start observing and modeling planet spectra on the day side, morning and evening side, and even the night side, as if these are stellar spectra, with detailed information on temperature pressure profiles, abundances, and wind circulation. In the middle, just an example, we can also start to measure isotope ratios in planet atmospheres as a new probe of planet formation process, but also possibly atmospheric loss processes. In particular, I think HDO over water ratio is very interesting, something we think we can actually probe with MATIS for Proxima b. And we are actually, in my group, working very hard now to apply such observations first to hot Jupiters, see what isotopes of which molecules we can start to measure now already. We have a very nice result already, but I cannot share that now. In the orange pinkish circle on the right, you can see, I think, the ultimate science case. Can we detect molecular oxygen in the atmosphere of an Earth-like planet transiting a nearby late M dwarf? Now, this will certainly be challenging, possibly needing several dozens of nights of observing time. So this will be really at the limit of what the ELTs could be doing. However, luckily, there is also another way of probing atmospheres, and that is also very nice, and that is combining high dispersion spectroscopy with direct imaging. Now, this is an idea that has been around for quite a while now, being invented and reinvented several times. In blue here, on the left, you see a typical direct image of a planet at the bottom. This is clearly identified in the direct image as a planet, but it's quite far from the host star, you can see. What you would like to do now is whether to find out whether there are planets much closer to the host star. But this is difficult because all these smudges, there is these quasi-static speckles caused by instrumental and atmospheric effects. Now, from the image itself, there is no way to find out what is a speckle of starlight or what could be a planet. However, when we have detailed spectral information, we could actually clearly separate a planet from a starlight because the spectrum of the planet will be very different from the spectrum of a star. Now, let me explain this in simple terms here on the right. This is actually a white light image from Beta Pictoris, a very famous exoplanet system. One does not see the planet now, only the star in the middle. The planet is somewhere in the bottom right. And because the image is completely swamped by starlight. However, these are data actually from Symphony. This is an integral field spectrograph, meaning that we have an RS4000 spectrum of each pixel in this image. And we can actually remove the star spectrum from each pixel very accurately because it should be everywhere exactly the same. And then we cross-correlated each pixel with a model planet spectrum to see whether there's any planet signal anywhere. And then a bit of magic, the starlight is gone everywhere, and we see a very strong signal from the planet, now at a final contrast of 100,000 or so. Now here you see two examples where this technique worked very well. The first one on the left is again Beta Pictoris B planet, but now at very high spectral resolution of 100,000, taken with a slit. Within white, the carbon monoxide signal, with on the horizontal axis the velocity and on the vertical axis the position along the slit. The star position, there's nothing to see, but at the expected planet position, there is a clear signal. It's blue shifted by about 15 kilometers per second due to the orbital motion of the planet, and significantly broadened due to the spin rotation of the planet at 25 kilometers per second. That actually corresponds to a length of day of about 8 hours or so. Now on the right, we see a recent result on H-alpha emission of 2 accretion planets in the very young PDS-70 system. It's also very, very exciting. Now, there are many important instrument developments that will bring this technique further. such as a combination of sphere with high-resolution spectrographs on the VLT, but also other projects at Subaru, Magellan, and Keck. But again, the real game changer here will be MATIS on the European ELT. Hopefully, we'll be ready in about 7 years or so. For our nearest neighbor, we calculate Proxima b that we can actually able to detect, if present, water, methane, and CO2, and even the isotopolog HDO. Now, when we have high res, we could take this to the optical and near infrared and target the reflected light from the planet, and also actually molecular oxygen. So if this is really an Earth-like planet with an Earth-like atmosphere, we could really characterize it extremely well. Now, this is my last slide already. I want to end with this one slide with a much more distant outlook, at least 15 years from now or even longer. What about the true Earth analogs around Sun-like stars? Because with the ELT, we can do Earth-like planets like Proxima b, maybe the TRAPPIST-1 planets around very late M dwarfs, but we cannot do it around Sun-like stars. Just the contrast is just too much. It's just outside the realm of the ELTs. So we need to do something else. Either a high contrast imaging space mission. NASA is already studying those, LUVOIR or HABEX, or even an infrared space interferometry mission. Now, this sounds like the very distant future, and why are we thinking about this now? But we really need to do that. ESA is already making plans for the long-term future, and we really think ESA should play an active role in this. It seems far away, but we really need to start now if we want this dream to come through. I want to thank my group over the years, all the people that have worked with me, and I thank you very much for listening in.
Thank you so much, Ignas. This was really very broad overview of the recent activities in this field. I would like to invite the speakers to ask questions. In the meantime, I have one. You mentioned these accreting planets. What do you mean exactly for that? What could be these accreting planets?
Yeah, so accreting planets. So these are still planets which are actually forming. So I can, don't know, but I can go back in the, yeah, here it is. So it's here on the right here. So this is the PDS-70 system. This is a system that has been studied with ALMA really well, and ALMA showed that there is actually a ring of gas, and so there is actually a gap in the middle, and it was thought, oh, there's probably planets forming there. And then very deep images showed that indeed there was one planet that is the brightest here, planet B, to be present. So there is indeed that's about a Jupiter, Mars, or a little bit more massive planet. And what we now have shown that there is actually a second planet there, and not only that, this is actually an H alpha image. So this is actually emission that is coming from the direct region around the planet. It's heated by shocks, and this is actually from the gas that is still flowing onto the planet. Yeah, does that make sense?
Yes, I see. Thank you very much. We are having more questions. Why don't you, Amaury, ask yourself this question, please?
Hi, Ignas. Yeah, I was just caught by the image, and I was wondering, are the two planets at the same orbital separation from the star?
No, that looks a little bit like that, but that has to do with the orientation, the inclination of the system. So actually, PDS-B is very near the long axis, and C is more closer to the shorter axis. C is, but they are in resonance. I think it's a 2-to-1 resonance, but I'm not sure.
Thanks.
Jorge, please go on with your question.
Oh, thank you. I don't know if the question might be a bit naive, but anyway, so my question, if there is any possibility to have or server-like analogs, not around sun-like stars, but around different stars, like, for example, around white dwarfs.
Sorry, was your question whether there could be life around white dwarfs?
Yes, it could be any air-like analog around white dwarf.
Yeah, so of course we don't know anything about this. that would be the short question. So there are many ways to actually approach this question. When you have to be, one of the premises you have to think about when we at some point in the future will search for life outside the solar system is, yeah, there can be life anywhere, but you have to be able to actually recognize it. So that's why sort of the habitable zone has been defined, because we think liquid water on the surface is needed to make a habitat that is so influencing the planet atmosphere that we could be able to actually see it from light years distance. Of course, there could be many forms of life under the ice somewhere, but yeah, we will never be able to find that at very large distances. Now, your particular question on white dwarfs, there are some ideas that white dwarfs could also have an actual habitable zone. Especially now, there are some first indications that planets are found around white dwarfs. And then the question is, yeah, could there be rocky planets which have an atmosphere, and could they host life? It would not be the first place I would look, but you know, it would be possible maybe. Who knows?
Thank you.
Okay, thank you, Ignas. I think we have to move on with the program. Thank you so much again for your nice talk. And I would like to ask Amaury to share his screen, please.
Okay.
So the next talk is by Amaury Triaud, Exoplanet Atmospheres. Oh, changed a little bit. Okay, Exoplanet Diversity, Planet, and Planet Formation. Okay, you can proceed.
Yeah.
Thank you.
Thanks, Gregory. I'd like to also thank all the organizers for bringing exoplanets to your meeting and allowing all three of us to talk about, I think, a topic that is a passion of ours. When Ignas, Artem, and I discussed early on, it was fairly clear that Ignas would spend a bit more time on atmospheres, talking about extraterrestrial biology. So I thought it would be interesting to focus on exoplanet diversity, which he briefly brushed upon, and the other big reason why we're searching for exoplanets, which is to understand the context of Earth within the many outcomes of nature. So one of the things that is interesting is that in antiquity, there was this concept of the plurality of world, a concept brought by Epicurus that everything is pretty much possible, and all sorts of planets, all sorts of size, mass, etc. And we know as physicists that not everything is strictly possible because we have physical laws that shape the natural world. However, within the exoplanet properties, it is strange that a lot of them do not correlate with one another. And so this has become, I think, one of the main discovery of the past 25 years is how diverse exoplanets are, how beyond our imagination nature really has been. And these are all the sorts of measurements that we make of exoplanets, and very few of them relate to one another. And we'll explore that a little, and I'll show how the study of various parameters that are displayed on the screen can allow us to glimpse at how planets form, looking at planetary systems now. I won't brush into disks and the planet forming, like in the case of PDS-70 that Ignas just showed. So briefly, there are two main methods that we use for detecting exoplanets. That's the first of them, radial velocity, where we measure the motion of the stellar light. So we don't see the planet directly, we infer its presence. The data here represents radial velocity on the vertical axis and time on the bottom axis. And the typical signal that we get, and it's in interesting to know this in order to appreciate the kind of results that we have, is that you get a signal, an amplitude of about 12.5 meters per second for a Jupiter analog on a Sun-like star. If you want to search for an Earth analog on a Sun-like star, this signal goes down to 9 centimeters per second. And this is extremely challenging to achieve, which explains some of the recent successes that happen not on Sun-like stars, but on stars much smaller than the Sun, like TRAPPIST-1. The summary of the results can often be shown in this one diagram, which is mass and orbital period. So mass in units of Jupiter and orbital period in units of years. We can see Venus and Earth at the bottom and the 4 gas giants of the solar system. And after 25 years of mass measurements, mostly through radio velocity measurements, you get this sort of picture. And that's where the diversity of exoplanet comes in, because most of the system, the vast majority of systems that we've discovered, are not like the solar system at all. There are various classes that are interesting here, hot Jupiters, but the high density that you see is a mistake. It's because those are the easiest to detect, and they only exist around 1 star in 200, roughly. We have the so-called cold Jupiters in that area. The survey is still not complete because we're reaching the precision of our instruments on the bottom and the extent of discovering planets. We've only been discovering planets for 25 years, and it takes 2 orbits typically to confirm one. But they're about 1 star in 8, roughly. And then we have this big group that Ignas alluded to of super-Earth and mini-Neptunes, which is staggering because about half of single Sun-like stars have a planet greater than the Earth, slightly shy of Neptune within Mercury's orbit. Half of the stars. This is a huge number. And just from that, it's fairly clear that if there is no dominant planet mechanism, or if there is, certainly the solar system is not part of it. It doesn't mean that the solar system is very special. We can still be part of a broader distribution, but it means that certainly what is within the solar system is not particularly representative of the rest. My personal view is that nature is extremely diverse. There might be something like 200 special characters that a planetary system have, and the solar system just picked 20 of those. As such, it's not very special. Like someone winning the lottery is not very special. There has to be someone, but in the same time, we're unique in a sense. In terms of precision, this distribution is shaped by the precision of the instrument. So the early instruments were about 10 meters per second, which you can see were barely sufficient to detect Jupiter, and they needed to operate for 25 years to find a Jupiter-like planet. So that explains the paucity of object on the top right of the graph. So 1 meter per second instruments came with HARPS in Chile and allowed the detection of the first super-Earth and mini-Neptunes. And now Espresso on the VLT is reaching to the 10-20 centimeter per second. But as you can see, the planets here are getting harder to detect because we're reaching stellar noise, which is a big hurdle in our quest to find more planets. Thanks to radio velocity, we can also measure the eccentricity of an orbit. That also shows how diverse, how different planetary systems are to the solar system. You can see that many of the gas giants that we could see in this diagram here, the cold gas giant at about between 1 and 10-year orbit that are there, more massive than Jupiter typically, also tend to be more eccentric than Jupiter. A lot of eccentricity, as you can see here. If we look at compact planetary systems like TRAPPIST-1, they tend to be all exactly at 0 or very close to 0 that you see as a line of points. But by and large, planets seem to be fairly eccentric, and it's hard to explain completely at the moment, and we're still investigating some of it. The one thing that we know is the envelope. The envelope here is fairly simple to calculate. If you take a Roche limit and calculate the periastron passage of a planet, and you find that nothing should be able to exist left of that line, and indeed the vast majority of planets conform to that, modulo, of course, a few changes in terms of composition, liquid versus solid compositions. Now I'm bringing up the second method that complements this sort of picture of diversity, which is the transit method, where we wait for the planet to pass in front of the star. It acts both as a detection method, but also as a characterization method for the atmosphere, as Ignas alluded to. What we measure in practice is this. So you see here the flux of a star. This is TRAPPIST-1, which has 3 planets passing in front of it. And as the flux drop, you have 2 planets coming in, then a third planet coming in, and then finally each planet coming out, the first, second, and third, creating a rather beautiful signal. The depth of this event gives us the size, which is in relation to the star to the squared power. Which explains why small stars are very handy, because you rapidly gain an amplitude, an amplification of the transit signal. And similarly, the reason why people have been focusing on such small stars is because the atmosphere gets a similar amplification. You can see here the depth of transit as a function of wavelength, which is the depth itself, and then a small additive factor, which includes the radius of the planet, the scale height, h, and the radius of the star to the squared power. So by focusing on a small star, you both amplify the detection of your planet, but also the detection of its atmosphere through transits. And that shows that exoplanet diversity at the beginning was often seen as, whoa, it's beautiful. We have planets that are very different from one another. But it became more now, like the focus is changing to, well, let's use that diversity to our advantage. And certain classes of planets allow investigations that others do not. And for instance, planets around very low mass stars allow to detect atmospheres of rocky planets, whereas around sun-like stars, we would not be able to at the moment. Thanks to transits, we measure radii, and here's the mass radius plot that we can find. You can see that compared to the solar system is nicely nestled within a broader distribution in this case, but also that there is a continuum. There doesn't seem to be a particular break throughout. There is just one, and I'll make a correction on the next slide, but by and large, almost every mass and radius along a line is possible. What is visible also from this diagram is that for a given mass, you can have almost a change of 1 order of magnitude in radius, and similarly for a certain radius, a change of 1 order of magnitude in mass, which is quite puzzling. And for instance, you have planets on the top left corner, so-called super puffs, which are really fairly low mass, but also have very large radii, which are hard to explain. So there's still quite a lot to understand here. Part of this dispersion is also caused by measurement uncertainty, and hopefully we will be reducing those. As we move towards more rocky, fully rocky planets at the bottom left, where you see Venus and Earth again, the dispersion looks much smaller once very tight uncertainties are shown, and I expect Artem will show you recent results on TRAPPIST-1 around there. So the one difference that I noted that there was like this population of super Earth and mini Neptunes. And the reason we call them of 2 classes is that we suspected for a while that some were rocky and others were not. And in fact, this was confirmed fairly recently. This is a reanalysis of some of the Kepler results, where you see radius as a function of orbital period, so Earth at the bottom and Neptune at the top. And you can see that there is a gap between some of the planets. And the idea is that many of the mini Neptunes, so small version of Neptunes, are born with fairly large rocky or icy cores. It looks like they're mainly rocky at the moment, and a small fraction of hydrogen and helium of order a few percentage, which disappears either due to irradiation from the star or due to irradiation from a young hot planet, which evaporates its own atmosphere. And then they drop through this gap in a sort of Hertzsprung diagram in reverse, where there is a quick transition between mini Neptunes and super Earth. A transit configuration also allows us to do other type of investigation. And one of them, for instance, which has been helpful in learning about exoplanet diversity, is the Rossiter-McLaughlin effect, where if your star is rotating, you'll first be covering the blue shifted side of the star and then progressively the red shifted side of the star, meaning that you can have a color effect in your radial velocity, in your spectrum. And the amount of time and the timing of when you cover the blue compared to the red side of the star means that you can measure the orbital inclination with respect to the stellar projected inclination. And that means that we could find that several planets were on coplanar orbits, like the solar system is, but a large fraction of them also are on inclined orbits. Typically, about 30% of the hot Jupiters are on inclined orbits. And recently, we have started to see a few super Earths as well that occupy orbits that are not coplanar to the stellar equator, which is sort of surprising. There too, this is a line of inquiry in order to see if this shows us something about planet formation or processes post-formation of the planet, and how much of the star also influences the planetary orbits. But this is a very nice and active subfield within exoplanet. So going back to this diagram here, how do true Earth analogs fare? Well, at the moment, you can see there are not many points where Earth and Venus are. Kepler also failed to detect many systems, but our non-detections of a true Earth analog still allows us to place limits. And at the moment, it's likely that true Earth analog are about 1 in 10 stars. It might be lower than that. Obviously, it cannot be better than 1 in 5. And this shows that true Earths around single sun-like stars are fairly rare, but not extremely rare. Extremely rare. Now, one thing that is important in appreciating exoplanet diversity is that in this diagram here is 2-dimensional, but in fact, there is a 3rd dimension here popping out of the bottom left, which would be the sort of stellar mass. And we forget that when we look at the sun, we always imagine that this is the most natural star, but in fact, single sun-like stars are fairly rare in our galaxy. This is the census of the 10 parsecs around the sun. And you can see typically true Earths are being sought after around stars that are 1 plus or minus 0.1 solar mass star. And these only are contained within about 15% of the total stellar content of our galaxy. And if we remove binaries, this only concerns 7 to 8%. And so the diagram and all the diversity that I showed you earlier only concerns less than 10% of the stellar content of our galaxy, which is rather small. And this is why a lot of people now are interested in low mass stars, because you can see they are the majority. And if there is one number I think that you should take away from my presentation here, is that 50% of stars are binary systems, and we know not much about planet formation around those. 50% of stars have masses less than a quarter of the sun's, and we don't know much about planet formation around those, and I will cover some of that afterwards. And about 50% of single sun-like stars have a super Earth or a mini Neptune. And this shows how sort of strange the solar system may look within all of the realization that nature managed to produce. And my talk's early conclusion is that it's important to look at various environments that are different from single sun-like stars if we want to study planet formation, understand how planets form as a sort of universal law, trying to understand the context of Earth, but also to search for extraterrestrial biology, because I think the real question is not so much whether there is biology elsewhere, but how often it happens and under which condition. Those are far more interesting scientific questions, in which case we have to include other types of stars. So typical environment that is different are planets orbiting very low mass stars that Artem will talk about afterwards. I will briefly mention that now. Circumbinary planets, a topic that I'm investigating quite a lot at the moment, and I will spend a bit of time on this topic. But I don't want to overlook also polluted white dwarfs. So in a question, we mentioned briefly white dwarfs, and some white dwarfs show metal pollution that indicates planetary material around them, which allows us to study the composition, the typical composition of other asteroid and debris disks around stars. And now we're moving also to the study of different galactic environments, trying to find if planets are altered, planet distributions are altered within open clusters, within young stars, or as a function of metallicity or location in the galaxy. So the first topic is around low mass stars. The reason low mass stars are important is because of this. Like, if I think any physicist wants to find a sort of universal process, and any good physical law will apply across orders of magnitude. And you can see that most detections of planets that have radii less than twice the radius of the Earth were found around sun-like stars, and very few around the bottom of the main sequence. And it's very difficult to try to find planets around 10 solar mass stars for two reasons. One, they're too big and don't have enough lines for most of the detection methods, but also they live such short lives that it's hard to see how planets one could form, but also survive around them. So we have to go down in a way if we want to study planet formation as a function of stellar mass across orders of magnitude. Now we know that stars at the bottom of the main sequence, at the bottom of this plot here, are the most numerous, and you can see that there are not many planets. And the reason is not that there are very few planets there, but rather because most attention have focused on the top of the diagram here. And if we take the sort of a guesstimate from the few surveys that did look at the lowest mass stars, we find that the occurrence rates of planets are staggeringly high compared to single sun-like stars. And for instance, here we're within 15% of a sun-like star. There were two surveys, the TRAPPIST SPECULOOS survey that found TRAPPIST-1, which had 50 stars, and found TRAPPIST-1. And within the Kepler mission, there were about 100 stars, which led to 2 detections. And this implies an occurrence rate of about 30 to 45% for Earth-like planets within a 6-day orbit, which is rather important. Another way to look at the problem is also to search and see Proxima Centauri b, the closest system to the Earth, which is around a very low mass star. And its probability of transit, it's a habitable Earth mass planet, and its probability of transit is 1.5%, meaning that if the occurrence rate eta of habitable planets around such stars is 100%, then one needs to survey 66 stars. Within the volume where TRAPPIST-1 is located, which is at 12 parsecs, there are about 170 stars that are less than 15% of the mass of the Sun, 85 in each hemisphere, which just from that very detection implies a sort of occurrence rate compatible with 80% of low mass stars having such Earth mass habitable zone planet, which is extraordinarily high. So reality might be a bit lower, but those high numbers are an invitation to observe more because the stakes cannot be higher in this case. And so if we look back at this diagram here, we have 3 times as many stars at the right-hand side here, and we may have 3 times as many Earth-like planets around those, meaning that the most common Earth-like planets are not around Sun-like stars, but maybe around the bottom of the main sequence. Implying that in order to study the context of Earth, our understanding about Earth-like planet formation, we cannot avoid going around and studying M dwarfs. So the final topic I want to bring up is about CIRCUMBINARY in a project that is being supported now by the European Research Council called BBOP, as binaries escorted by orbiting planets. In this configuration, we have 2 stars at the center and a planet orbiting both. And you can see the white circle here is an area where planets cannot exist because their orbits would be unstable. But beyond about 4 to 5 times the binary orbital period, planets have fine and stable orbits on the long term. The reason circumbinary planets are interesting is in the context of core accretion, which remains the primary method through which we think planets are forming. You see the bottom equation here is the rate of change of mass as a function of time. It comes as a function of the surface density of the disk, the orbital velocity, and then the cross-section of the planet. But what's important is the 1 plus theta here, where theta is the Safronov number. Safronov number is itself the escape velocity of your protoplanet divided by the dispersion velocity of the disk. And in a disk that is around a single star, the disks are very laminar, and this bottom term is very small, meaning that the Safronov number is very high, and dm over dt is extremely high, leading to planet formation. When you place 2 stars at the center instead of just 1, you increase the disk dispersion velocity, meaning that the Safronov number decreases extremely rapidly, and your planet formation is stifled. And in fact, more accurate simulations show that about within 50 separation of the binary, you should not expect planet formation to take place, which for most close binaries means that there would be no planet formation within 10 AU of the system, which is extremely like a wide area where nothing can form, and most planets ought to form very far out. And yet we find circumbinary planets. So this is the same planet mass orbital period diagram. In white, you see the same sort of single radio velocity detection around single stars. And in gray, you find circumbinary planets. The circles are for Kepler, and in the top right corner, there is a diamond for a more uncertain detection. And you can see that those are well within 10 AU of their stars. So how did they form? And how can those planets form in such a hostile environment? And the key question was also trying to find out how frequently do these planets form. And so for that, what's important is to understand how the gray dots here were detected. They were detected by the Kepler mission, which uses only photometry. And you can see here eclipses of the binary. You see the eclipses in blue and orange, the primary and secondary eclipse. And then there are 3 transits of the planet. And so you need a very collineated plane where the binary has to be perpendicular to your line of to the plane of the sky in order for eclipses to happen, but so does the planet, meaning that you are biased towards a coplanar configuration. And assuming full coplanarity, like a coplanarity of 0 plus or minus 0, then you can extract from the few measurements, a few detections that have been made by Kepler that the occurrence rate of gas giants in circumbinary orbits is of order 10 to 15%, which is very similar to the numbers that we see around single sun-like stars, which is rather puzzling because planet formation is thought to be harder. Now, that's only the start, because we're not totally certain that planets have to be extremely coplanar around such binaries. And in fact, as soon as your planet is slightly misaligned, it will start circulating compared to the binary plane, meaning that sometimes the red orbits that you see on the screen of the planet's circulation and the binary orbit is in black, that only when the red lines cross the black line can you have transits possible. And so you start losing planet fairly rapidly as soon as your planet is circulating, because there are times when it can transit and times where it can't transit. And you can correct your planet abundance rates as a function of the delta I, the spread of mutual inclination, whether it's 0 plus or minus 5, or plus or minus 10, or plus or minus 20. And you can see how the circumbinary planet abundance on the left-hand side can increase very dramatically for just small change in the variance of the inclination. At the moment, we can measure that this variance from the Kepler results is about 3 degrees, which implies that even the rates that I was alluding to earlier might be underestimated by a factor of 1.5 to 2, just because of that mutual inclination. And so we started to search for these planets using radio velocities. And at the moment, this is very preliminary results after 2 years of a survey. We still need to confirm those candidates, and I expect 1/3 to 2/3 of these red dots to disappear after a while, but we're starting to see some signals. And at the moment, allowing for some non-detection, so from some false positive rate, we see an occurrence rate for circumbinary gas giants to be between 14 and 28%, which implies slightly higher, but probably compatible with a single sun-like star. And we also see that we have a lack of high mass gas giant. You can see that all detections almost are below 1 Jupiter mass, which is rather interesting because it's shedding light on planet formation processes in an empirical way, in an environment where at the center you still have a sun-like star, but it's been transformed by the presence of a very low mass star in orbit around it. And so eventually the idea will be to compare one-to-one distributions, like you can do, or the same with other galactic environments, for instance, the distribution in mass, in orbital period, eccentricity, etc. All those measurements that I alluded to at the beginning that form the diversity of exoplanet. And by comparing one setup or one environment versus the other, try to make sense of how planets form and appreciate how the solar system may have come to be. So in overall, my conclusions are such to support observations in alternate environments to single sun-like stars, because those are very biased, small fraction of our galaxy. And I think it's important and interesting to explore the rest. And obviously, if you're a modeler, try to model planet formation taking alternatives to single sun-like stars and produce models that say, for instance, if you have a binary, you expect half as many planets or twice as many planets, because this is fairly easy to measure. And so before taking question, I'll just thank all my collaborators here, the students that are working with me at the moment, and the teams behind Bebop and SPECULOOS that have shaped many of my views. And thanks a lot for your attention.
Thank you so much, Marie. We are ready to the questions. In the meantime, I would also like to ask one. Of course, one would be a comment, one question. So regarding the low mass stars, in the context of possible life signatures, there is, of course, a debate that such stars are not so much stable as the sun. They're very active, and we're looking at particularly close by planets. Therefore, it would be not possibly the best place in terms of stability of the conditions for life to develop. But well, I think this is well understood, and the only way to search for this is to increase our instrumental possibilities, right? But I would like to ask a little bit a different question. What about really planet formation in the relatively early universe, let's say, because we're used in cosmology to speak about very formation of stars at redshifts about 50, 30, which implies, I mean, millions years after the Big Bang, roughly speaking. Of course, from the observational viewpoint, we're limited to very, very close by regions near the sun in our galaxy. But generally speaking, are you expecting also planet formation along the star formation, even different from what we currently see?
Yeah, that's a very good question. Just to address your early comment about low mass stars, I agree. I see many of the restrictions that low mass stars can have. They have a very chaotic youth. But I'd say at the moment, Earth-like planets around low mass stars, and I'm sure Artem will echo some what I say, are the only ones that we can study the atmosphere of at the moment. And I think it's better that we start now studying those because we can, and they might be the most frequent ones because of two reasons. One, if it turns out that they have atmospheres and it turns out that they have life, then we have discovered it earlier. But obviously, if they don't, then because this is the largest population of Earth-like planets, we already would know that at most 1 in 10 rocky planets in the galaxy has life, which I think is a far more interesting answer. It's bringing how it's starting to answer how frequently is there biology in the cosmos, how ubiquitous it is. So even a non-detection around low mass stars is of very high interest because true Earth analog can only be done in the late 30s, 2030s or 40s, whereas we can start now around TRAPPIST-1. Concerning galactic environments or other environments, I don't think there are many models that are looking at redshift of 50 to make planets. What I can say is that we can search environments within the galaxy, like the halo, the thick disk, which have much older stars or low mass, low metallicity stars. In terms of metallicity, we know that gas giants primarily form around metal-rich stars. And it's a very steep function. In fact, there's been an entire project on HARPS focusing on stars that were less metal-rich than the sun, and they found, I think, less than metallicity of 0.2, I think. And they didn't find a single gas giant within the sample. However, they did still find super Earth and mini Neptunes, showing that this didn't prevent planet formation there. There's a few investigations in globular clusters as well, which are notably old, and no planets were found there. However, it's unclear whether it's due to the low metallicity environments of a globular cluster or due to the rather destructive dynamical environment of a globular cluster, where exchange of angular momentum between stars and planets would be a lot easier and lead to severe disruptions. I think that now that we have a full sky mission like TESS, in fact, it's a project that I'm starting to work on. we'll be able to have a number of planets around halo and thick disk stars, and at this stage we'll have a better picture on how different and how similar they are currently, and start answering your question about early universe, but probably not redshift 50 though.
Sure. Thank you so much. We have a question from Moderator, please go on.
Thank you. I'm curious, we'd like to know which is the main channel for the formation of the planets in escorting binaries.
Yeah, at the moment, the main thought is that they do form far and migrate in. At least what we are fairly certain is that the few detections around second binary planets highlight that both gas giants and super-Earth mini Neptunes can migrate. So from far out, like sort of 10 AU towards the star, which was not a given. We're still unclear around single stars whether planets can form in situ or fairly close to the star and stay there, whether they have to form far and then come in. So I think the study of second binary planets shows that migration is a possibility. Now there's also some work trying to find out whether planets can form within these 10 AUs, because at the moment, the problem of second binary planets show that there is an issue of agglomeration of a planet. It's like this dispersion shows us that the planets would not be created. However, if they do manage to form within this 10 AU, and some models seem to imply that they can in some ways, then it's telling us that maybe a similar, like a different, process to what we currently take for granted takes place on how dust accumulates into larger bodies. For instance, a few processes like streaming instabilities have been investigated, which can make you jump from like sort of dust particle to planetesimal in one go. Processes similar to that might be important in circumbinary disk, and those might highlight how important they are. Whereas around single stars, we don't know, like we have various models that we juggle with. The advantage of a second binary environment is that you can remove one scenario, say co-accretion, allowing us to study other formation scenarios, like and now there are various ones like streaming instabilities, pebble accretion, or a mixture of all of those. I hope I answered correctly, Jorge.
Yes, thank you, Amaury. Thank you.
Okay, thank you very much once more, Amaury, for this nice talk. We are going to the next talk. Artem Burdanov, can you please share your screen? Artem is going to speak about exploring the nearest ultra-cool white dwarfs or terrestrial exoplanets. Please, you may start.
Good morning, good afternoon, or good evening, everyone. I would also like to thank the organizers for giving me an opportunity to present this talk, and I also thank participants for their attention. I work in detection and characterization of exoplanets, and today I would like to present you a talk which is dedicated to the search for terrestrial exoplanets around so-called ultra-cool dwarfs. I would like to start with a brief outline of my presentation. So first, I'll provide some general information about ultra-cool dwarfs and scientific rationale for exoplanet search around such type of objects. Then I will speak about photometric searches for transiting terrestrial planets around ultra-cool dwarfs, and my focus will be on the SPECULOOS survey, in which I'm lucky to participate. And in the end, of course, I will provide a summary. So what are ultra-cool dwarfs? Ultra-cool dwarfs, or UCDs for short, are traditionally defined as dwarf stars and brown dwarfs, which have effective temperatures less than 2,700 Kelvin, luminosities less than 1,000th of solar, and spectral types later than M6, including L, T, and Y dwarfs. In this diagram, you can see a bottom of the main sequence, which contains ultra-cool dwarfs. Effective temperature in kelvins is on x-axis, and stellar radius in solar unit is on y-axis. These objects have masses below tenths of a solar mass, extending below the hydrogen burning minimum mass. and their radii are about 1/10 of a solar, what is basically size of Jupiter. In this figure, you can see a relative size of Sun, M, L, and T dwarfs, and Jupiter. Regarding atmospheres, ultracooled dwarfs are very rich in molecular gases and condensed refractory species, and they produce very complex spectral energy distributions. And these distributions are very strongly influenced by the composition and chemistry. And this distribution peaks at near and mid-infrared wavelengths. Here you can see a spectral energy distribution of Sun and ultracooled dwarf TRAPPIST-1, which has a spectral type M8. Ultracooled dwarfs are fully convective and well mixed in their interior composition, and convection coupled with their very low fusion rates gives lifetimes of tens of trillions of years for stellar ultracooled dwarfs. And for substellars, ultracooled dwarfs, they persist indefinitely with ever decreasing temperatures and luminosities. And another remarkable thing about ultracooled dwarfs is that they are, in fact, most abundant in solar neighborhood. So ratio of ultracooled dwarfs to G dwarfs is larger than 5:1. And you've already seen this figure. Here on the right, here you can see stellar and substellar objects within 10 parsecs as a function of mass discovered by the RACONS project. And the blue bar represent white dwarfs in the vicinity of Sun. Blue bars represent stars of spectral types A, F, G, and K. And these red bars, they represent a very abundant red dwarfs of spectral type M that dominate the solar neighborhood. And to date, more than 4,000 exoplanets are known, and most of them have been discovered around F, G, and K dwarfs. And here you can see a number of confirmed exoplanets as a function of effective temperature of a host star, which is on x-axis. And despite ultracooled dwarfs represent a significant fraction of the galactic population and abundant around Sun, their planetary population is still basically uncharted territory. And as of today, only a handful of exoplanets have been found around such hosts. They were discovered using 5 different methods. Here you can see names of these methods and number of planets discovered by them. So these methods are direct imaging, microlensing, radial velocity, astrometry, and transit photometry. As you can see, microlensing technique is quite powerful. It detected 9 planets, but unfortunately, such detections are usually, well, are always one-time events, and not much can be investigated about the planet except its mass. However, transit method is a powerful discovery method, and moreover, it's a very powerful characterization technique. To remind you, when an exoplanet passes in front of its star, it becomes possible to notice the change in the incoming flux from the host star because the planet blocks some part of the light from the star. And a change of flux from the star with time is called a light curve, and it is presented here. And fractional change of flux during the transit is called transit depth, and it depends on the size ratio of the planet and its host star. And a transiting light curve contains a lot of information. By measuring the transit depth and knowing stellar radius, for example, from stellar evolution models, we can get a radius of the planet. We can also infer planetary orbital inclination. We can assess stellar density, which affects the shape of the transit light curve. We can also obtain an orbital period of the planet if at least we have 2 consecutive transits. Also, transit method can be used as a search technique if you obtain light curves of many stars in the field, and then if you search for the specific transit signals in their light curves. And this method is highly complementary by the radial velocity method that can provide us with a mass estimation of the planet. Also, during an exoplanet transit, some light from the host star is actually filtered and transmitted through the planetary atmosphere. And such filtered light carries fingerprints of the exoplanet. And depending on the atmospheric properties of the planet, its transit will be different in different wavelengths. And dependence of a transit depth as a function of wavelength is called a transmission spectrum. Here you can see an example of such a spectrum. And by analyzing this, one can learn about chemical and physical properties of the atmosphere. Mostly gas giants are objects of these studies because they are large and they are very hot. Here you can see example of WASP-19b transmission spectrum. But the logical question is, what about atmospheric research of terrestrial exoplanets? And the answer is, it's not easy. Among few things, amplitude of the signal for major spectral features crucially depends on the transit depth, which in its turn depends on the sizes of host star and planet. And in case of a sun-like star and Earth-like planet, here on the left, transit depth is less than 1/100%. And here you can see a schematic view of the transit light. But in a case of a smaller star, the very same Earth-like planet will result in a much larger transit depth, which could be around 1%. So exactly here, properties of ultra-cool dwarfs come in handy. If there is a planet around an ultra-cool dwarf, not only we have an increased transit depth, but also the probability of a transit and number of possible transits that we can possibly observe from Earth. They all drastically increase in this ultra-cool dwarf regime. And here you can see probability of a transit in blue, transit depth in red, and number of transits observable per year from ground in black. And green zone represents area of ultra-cool dwarfs, what is basically below 1/10 of a solar mass. Here you can see position of a habitable zone around main sequence stars. Habitable zone is a region around a star where an Earth-like planet can retain water in liquid form on its atmosphere, on its surface, if planet has an atmosphere. At 1 astronomical unit, you can see Earth in the habitable zone of Sun. But once we consider cooler and cooler stars, habitable zone comes closer and closer to a star. And ultra-cool dwarfs, located here, they harbor a habitable zone that is much closer to them than that of a solar-type star, what makes transits of potentially habitable planets there more likely and more frequent. Quite a few studies have focused on the James Webb Space Telescope and European Extremely Large Telescope, and they are used for atmospheric characterization of terrestrial exoplanets. And all these studies agree on the fact that the best suitable target for atmospheric characterization and even biosignatures detection would be a terrestrial transiting planet around one of the nearest ultra-cool dwarfs. Hopefully, these facilities will be operational soon and there will be no more delays, but in any case, we need targets for them. Here I will talk about surveys, photometric surveys, which aimed and still aim to detect such planets. One of the first surveys that tried to explore transiting exoplanets around ultra-cool dwarfs was conducted with the Peary-Tel telescope. Here you can see how it looks like. It was equipped with an X2 mass survey detector, and in principle, it's X2 mass survey telescope. The project observed 13 ultra-cool dwarfs in 2004 and 2005 for a period of 10 months. Here you can see some light curves that were reported. Unfortunately, there were no detections, and partially it's because of the precision, which is about 2%, 1–2%, and also they're observing cadence, observing mode. Observations were done for 10 months, but not continuously, with some gaps, and I think it's average on 30 minutes or 1 hour per night only. Back in 2011, another survey started to search for planets around ultra-cool dwarfs. And a prototype mini-survey on TRAPPIST South telescope was initiated. TRAPPIST South, depicted here, is a 60-centimeter Ricci-Chrétien telescope that has been installed in Isola Cilia Observatory in the Chilean Atacama Desert. The telescope is operational, still doing observations, and it is equipped with a 2K by 2K thermoelectrically cooled back-illuminated CCD camera, which offers a quite good sensitivity in the near-infrared. And I remind you that spectral energy distributions of ultra-cold dwarfs peak in the near-infrared. It has a field of view of 22 by 22 arc minutes and pixel scale of 0.6 arc seconds per pixel. And this prototype survey targeted 50 among the brightest southern ultra-cool dwarfs with K magnitudes from 5 to 11 and uniformly distributed in terms of spectral type and sky position. Its concept was quite simple, though challenging. It's just to monitor each ultra-cool dwarf during at least 100 hours, and these 100 hours spread over several nights. And the initial goal was to assess the typical photometric precision that can be reached with such equipment for such kind of targets, and obtain detecting thresholds for terrestrial planets around ultra-cool dwarfs. And in the end of 2015, TRAPPIST telescope discovered first transits of planets around a middle-aged M8-type dwarf, which is called TRAPPIST-1 now. And later transits were confirmed by many ground-based and space facilities. This nearby star, TRAPPIST-1, is orbited by 7 transiting nearly Earth-sized planets in orbits from 1.5 to 19 days. Here on the left, you can see face-folded light curves from the Spitzer Space Telescope and system architecture on the right. On y-axis, it's change of flux, relative brightness, and here is time in fractions of the day. And here it's orbital separation in astronomical units. I'm sorry. All seven planets are temperate, and it means that their equilibrium temperatures are less than 400 Kelvin. And 3 of the planets, TRAPPIST-1e, F, and G, orbit in the habitable zone around the star. This habitable zone is in gray on this figure. These 7 planets form a near-resonant chain, and this particular configuration is remarkable as it greatly amplifies all the gravitational interactions between the planets there. And it results in transit timing variations. It means that sometimes transits happen a bit earlier or later than we expect them to happen. And dynamical modelings of these timing variations allows to constrain the masses of these planets. And from transit photometry, we have their sizes. And combined together, it can give us about density of these planets. That's why we are sure that they are Earth-like. I would like to know that TRAPPIST-1 star and actually other ultra-cool dwarfs are extremely faint in the visible. V magnitude of TRAPPIST-1 is 19, and J magnitude is 11. It means that radial velocity observations with conventional, and I mean optical spectrographs, are basically impossible. However, there are some new infrared that became operational recently, and they are also observing this system and other ultra-cool dwarfs. In this illustration, you can see the sizes of the TRAPPIST-1 planets' orbits compared to our solar system, and also sizes of the planets compared to the ones in our solar system. And as you can see, the system is very compact. But I would say what is the most fascinating is that the TRAPPIST-1 planets have become prime targets for atmospheric studies with James Webb Space Telescope and ELT. And if you'd like to learn more about this, I refer you to these publications. The TRAPPIST survey served as a prototype for a more ambitious search for exoplanets around ultra-cool dwarfs, which is called SPECULOOS. SPECULOOS stands for Search for Habitable Planets Eclipsing Ultra-Cool Stars. And it is an international project led by the University of Liège in Belgium and with participants from many other countries. Main concept of SPECULOOS is observing around 1,200 nearest ultra-cool dwarfs. And the main goal is to probe with more than 70% efficiency their inner habitable zone for transiting planets of Earth size and below. I'll be talking more about this survey in which I'm participating, but if you are interested in even more details, I refer you to these papers. So how to reach this goal? How to find planets in the habitable zone around ultra-cold dwarfs? Well, the answer is to design the survey wisely. Since ultra-cold dwarfs are distributed uniformly across the sky, it means that the survey should be targeted. So we should observe target one by one. Possible transits can be rather short. It means that continuous monitoring of targets is needed. And since ultra-cold dwarfs are rather faint in the optical range, it means that we need large telescopes, relatively large, of course, and detectors that is sensitive in the near infrared. And since we would like to explore efficiently the habitable zone and we don't want to miss anything, we need to observe each target quite a lot, up to 20 or 30 nights, and it depends on the spectral type. Here you can see a spatial distribution of the targets from the SPECULOOS input catalog. As you can see, they are located all over the sky. And here is another information about the target sample. So it consists of all the known nearby ultra-cold dwarfs with a K-band magnitude less than 12.5. It means that these targets are bright enough in the near infrared for possible future follow-up studies with James Webb. 87% of the targets are M-type stars from M7 to M9, and the rest is brown dwarfs. The figure on the left shows distribution as a function of the spectral type, and on the right as a function of the K magnitude. And this transit search could be done with 10 years of observations with a realistically small number of ground-based telescopes. So 4 in the southern hemisphere and 2, 3 in the northern, ideally 4 as well. SPECULOOS is based on 3 nodes. The southern ones, the SPECULOOS Southern Observatory, or SPECULOOS South, is operational from January 2019, and it is located at the Exoplanets Observatory, also in the Chilean Atacama Desert, as TRAPPIST South. It consists of 4 1-meter telescopes that will explore 600 ultra-cold dwarfs. The northern node of SPECULOOS, the SPECULOOS Northern Observatory, is located at the Teide Observatory. And there is 1 telescope so far, and it's operational since June 2019. Syntex, a new robotic telescope, is installed in Mexico and is identical to other SPECULOOS telescopes, and it will observe 50%. It will use 50% of its time to observe SPECULOOS targets. SPECULOOS South is located near NGTS, what stands for Next Generation Transit Survey, and it's 5 minutes drive from La Residencia in Paranal. And here you can see VLT platform and Vista telescope. This site is great for such survey because 80% of nights are dry, what is important when you observe in the near infrared, and around 78% of nights are photometric. It means that they're very, very clear. Here you can see 4 domes in the foreground and flat top of Cerro Amazonas mountain in the background. It's the place for the European Extremely Large Telescope. SPECULOOS North is located in the Teide Observatory, and here you can see the telescope and Teide volcano in the background, and this is actually very close to the master telescope. A few words about the hardware that we use. So all SPECULOOS telescopes are identical. They are 1-meter Ritchie-Chrétien telescopes. They have quite large domes, 6 meters in diameter. Mount that we use is a direct drive, and it has a special design with this pillar, which allows us not to have any meridian flip, so we can monitor the target entirely the whole night if it's visible. Combined focal ratio is f/8, and this optical tube assembly is made of steel, aluminum, and some carbon fiber components to compensate for thermal expansions during the night. And we have raw aluminum-coated mirrors. We do not use a classical near-infrared detector. We use thermoelectrically cooled camera with near-infrared optimized deeply depleted CCD detector. And here in blue, you can see CCD quantum efficiency. And as you can see, it is quite efficient in this near-infrared range. Field of view is smaller than the TRAPPIST. It's 12 by 12 arc minutes, and pixel scale is 0.3 arc seconds per pixel, but it's more than enough. It's very good for us, in fact, as usually we have only 1 ultra-cold dwarf target in our field of view. And we use standard Sloan filters with special filters called I+Z, which starts at 700 nanometers and then goes all the way to the red. And also blue blocking, which starts at around 550. A few words about the photometric precision. This figure shows measured fractional RMS of the differential light curve bin per 10 minutes of all the stars in the field during one night observed in 2018 as a function of the star's apparent magnitude in I+Z band. And this data, these blue dots, are compared with the noise model accounting for different contributions. And what we can see that data already match closely the noise model. So for bright unsaturated star, the precision is mostly limited by atmospheric scintillation. Boson noise dominates for intermediate brightness stars. And of course, sky background and dark current, sky background is significant for faint stars, but dark current is basically negligible. What is very good. So for intermediate brightness stars, we can achieve precision of a few millimag, and for bright unsaturated objects, it could be down to 0.5 millimagnitudes. And here you can see an example of SPECULOOS photometry on top. This is a differential light curve compared, obtained with SPECULOOS South Telescope, and it is compared to the light curve from the TESS Space Telescope. And on this axis, you have time, a fraction of day, and on this axis, you have relative flux. So TESS data was obtained with 2-minute cadence and then binned to 30 minutes. So these black dots are binned data, 30-minute bin data from SPECULOOS, and orange dots are from TESS. And as you can see, there is an excellent agreement between these two data sets. And these observations, I highlight again, they were obtained simultaneously. So far, no TRAPPIST-1-like systems have been discovered, but the telescopes are operational only for a few years. Here you can see some of the other discoveries. For example, an eclipsing brown dwarf binary with a period of 21 days, which also happened to be a double-blind. If you would like to read more, I refer you to this publication. And here you can see an eclipse that was observed with SPECULOOS of this eclipsing binary. Also, some fraction of the observing time on SPECULOOS telescope is dedicated to the follow-up observations of exoplanet candidates from NGTS, TESS, or K2. And for example, you can see reference here to a recently published planet discovered initially in the Kepler 2 data, Kepler 2-315. And here you can see this position on the diagram, which tells you how is promising a particular planet for atmospheric characterization with James Webb. So TRAPPIST-1b so far is the prime target, and for example, this K2-315b is just on the edge, so will be accessible with other with the next generation of telescopes. I would like to mention also other surveys. So another project also looking for transiting planets around ultra-cool dwarfs. For example, EDEN survey, which started just a few years ago, which reported no detection so far. But unlike SPECULOOS, EDEN has only limited access to the telescopes as they get some time on already existing facilities through the proposals. And their runs are usually typically 2 weeks long. There is also an extra transit survey, which is located at La Silla Observatory near TRAPPIST. And as far as I know, telescopes are being commissioned and no detections reported so far. There were also attempts to detect ultra-cool dwarfs with space missions. For example, Kepler and K2, no detections reported so far. There were also attempts to use Spitzer. For example, archival data of 44 nearby brown dwarfs were explored, also no detections. Last year, there was a proposal to observe a few ultra-cool dwarfs that are equator-on, and there is one unconfirmed candidate. And we also expect other surveys to emerge, to pop up in the next years, as there are a few publications where design considerations for such surveys are described. For example, this one by Tamburo and Muirhead. So I'm coming to a summary. these are the main takeaway points, in my opinion. So planetary population around ultra-cool dwarfs is mostly unexplored. Transiting planets around such targets are prime targets for atmospheric characterization with future facilities. And only one transiting system around ultra-cool dwarf is found so far. It's 7 planets around TRAPPIST-1 system. And SPECULOOS survey has started its operations. 1 brown dwarf eclipsing binary found so far, and photometric performance is very promising. And more surveys are expected to explore ultra-cool dwarfs for this type of planets. So stay tuned, and hopefully we'll hear more discoveries. Thank you.
Thank you, Artem, for your presentation. And I think also all the speakers of this session for perfect timing. So we have possibility for questions now, and in principle it can be asked maybe for all 3 speakers, since they covered somewhat supplementary topics. Therefore, I invite you. I can see questions in the chat yet. Maybe I would like to ask one question regarding this TRAPPIST-1 system. Of course, the fact that we observe it is a fact, but the dynamic chaos in particularly solar system is expected to play a role, and there is a possibility even for the Mercury to be ejected from our solar system due to interactions essentially among the planets. And what about such systems? How do you think they are stable? For how long time they can be stable? I mean, we see multiple planets and very near the host star. So what about stability of such systems?
Well, from what I know, we don't have a lot of examples of such systems, and in particular, TRAPPIST-1 is relatively stable, but we are currently only exploring some part of the TTV pattern of transit timing variations. So each observing seasons, many telescopes observe transits, and each transit contributes to one more point on this TTV analysis diagram. And with many years, I think it will be possible to say very confidently about their mass and overall dynamical stability. But from what I know, it is already quite stable. So yeah, that would be my answer.
Okay, thank you. Of course, we're talking about not the terms of few years stability, this is about millions and billions of years stability. But nevertheless, this could be an interesting question just for future studies, possibly. Okay, thank you. We have a question from Manuel Hoffman. For UCDs, the habitable zone is close to the star. So I would assume that planetary orbits are tidally locked. Is that the case? And what would be the expected temperature difference between day and night side?
Yeah, that's a good question. And actually, that's the point that I forgot to mention about TRAPPIST-1 planets. So indeed, very likely they are tidally locked. And even so for the planets B and C, which are very close to the host star, it might be very hot on the day side, but on the terminator or around that area, temperatures could be temperate. And the further we go from the star, actually the better temperature on day side appears to be. Of course, it depends on if those planets have atmospheres and what composition and physics of that atmosphere is. But there could be, of course, some difference in these in the day side and night side. Well, I would say maybe a few hundred Kelvin could be, but it also strongly depends on the atmosphere and the recirculation of heat there. Yeah, but it's an interesting question.
Okay, thank you. Are there any questions from the participants? We cannot see any. Okay, so thank you very much, Artem, and thank you all the previous speakers for your very interesting and stimulating talks. We have one more talk this morning, and this is somehow related to these topics. Costantino Sigismondi is going to speak about recent news from Betelgeuse star. You know, this is very massive star quite nearby, and it underwent some drastic change in the luminosity during recent months, and there was even a discussion about the possibility of some kind of artificial activity around the star. It was, of course, dismissed then, but nevertheless, I would like to invite Costantino to share his screen now.
Good morning to everybody. I am trying to enter in the condivision.
We can see your presentation. Possibly switch on your webcam, please.
Yes.
Okay. Thank you. You can go on.
So you see the presentation correctly?
Yes, you can put it full screen and
well,
please proceed.
Here.
Okay.
Okay. I have the screen, the second screen on the video.
Okay.
But nevertheless, what is Betelgeuse going to do next? Thank you for inviting me to this presentation. Also on behalf of Margherita Karowska, Remo Ruffini, Cesare Barbieri, Paolo Hochner, Luigi Bordoni, Fabio Mariuzza, Alessandro Amorin, Rod Stubbins, Ottmar Nickel, and Wolfgang Wohlmann. In this first slide, you see the front of the Uranometria of Johannes Bayer, and in the shoulder of the giant Orion, there is the star Alpha Orionis with Betelgeuse. Why I presented this image? Because the first point is that Betelgeuse is statistically less bright than Rigel, which is the beta of Orionis. In the second slide, that is now here, we see the last 3 years of light curve of Betelgeuse. On the left, we have the minimum of 2017, the minimum of 2018 after, and the minimum just now in August, September 2020. This second minimum was not expected at all. The characteristics of the first minima are gentle shape with some rebound in 2017, a regular one in 2018, reaching the maximum at the level of 0.4 magnitude, and a V-shaped one in 2020. The red cross are my observations made visually, and we see that they are systematically brighter, they estimate, than the red one, which are V. Johnson band, because of an effect which is the Purkinje effect. This effect is occurring to the naked eye when looking at red stars. Probably Johannes Bayer, choosing Betelgeuse as Alpha Orionis, had this similar effect. The minimum of August started in July and was observed in full daylight by us and by the satellite stereo A, who can aim to the star without being affected by the solar light. So these are the data in July showing that the minimum was going again. Betelgeuse is a semi-regular variable star of type C. Trying to move to the next. Okay. The image of Betelgeuse from European Southern Observatory showed in December 2019 almost half of the star covered by a cloud of dust. The nature of dust was proved by Dupree et al. in the 2020 studies in Astrophysical Journal with ultraviolet spectroscopy. In the time of our meeting dedicated to the Betelgeuse Great Minimum held in Pescara on January 17, 2020, many journals were speaking about a possible explosion of supernova. Betelgeuse is 20 solar masses star, so the end of its evolution is a supernova, type 2, but no alerts are possible from a supernova during 3 months, since the free fall time is 30 minutes. But there is a paper of George et al. Submitted to Astronomy and Astrophysics on the 30th of June of 2020, analyzing early warning signals indicating a critical transition in Betelgeuse, and the analysis is done on the last 30 years of the light curve of Betelgeuse. Here we see the light curve of 120 years of Betelgeuse, showing some bright maxima and some deep minima, like the last one in 2020, but there are other in 1985, 1947. George et al. Studied the last 30 years of observation of Betelgeuse, mainly visual observations. So the analysis held by them face with the Purkinje effect, which prevails in the visual observation, as we proved also with my personal data. And there is another problem, the problem of the May to July season, in which the star is not visible because immersed in the solar light. So they made some critical assumption in their statistical studies, and these assumptions have to be reconsidered in order to assess the effective change in the space of phase, in the phase space of the pulsation of Betelgeuse. According to them, it is ongoing a strong change in this behavior. Ptolemy in 150 after Christ wrote the Almagest, in which there is the catalog of bright stars, 1022 stars. There are only few stars of first magnitude. Among them there is Rigel, and Betelgeuse is classified as magnitude almost 1 minus. Statistically, this classification is coherent with the modern data. while for Johannes Bayer, we have to think to some Purkinje effect to this catalog. Now we go to the model of the geometrical model of the last event, the great minimum of February 2020 and the smaller minimum of July-August 2020. The star is represented as this big red circle. It is rotating according to Craig Wheeler. The rotation is 15 kilometers per second, a strong rotation for a star, like for a supergiant star, like Betelgeuse. And it is due to the merging of Betelgeuse with one solar mass star in the last 100,000 years. A great expulsion of dust occurred in December 2019, before this date, and the cloud moved out of the star, producing what we have seen in its light curve. And a second cloud was expelled in July 2020, closer to the limb of the star, producing again a secondary limb. When there are expulsions behind the star, but in our line of sight, there is an enhancement of the luminosity of the star because of backscattering. And this is the generation of the light curve due to a moving, growing, and fading exocloud. So we have the exocloud forming at the center, moving toward the limbs and fading, and the light curve consequently is drawn in the lower part of this view graph. Interesting is the behavior of Betelgeuse in infrared observation of Herschel Space Telescope. There are some spherically symmetric clouds that are going to hit a wall which is on the left side of the image, and this wall will be eaten in 5,000 years. So each of the shell is separated by the other by about 1,500 years. So maybe this is the difference between Ptolemy and Johannes Bayer observation. This is another possible explanation, but is another possible explanation for the change of Betelgeuse behavior to a period of dust expulsion of stellar wind, strong stellar wind, which may undergoing right now. We have to observe for knowing what is going on. The next observational season will expect another minimum in April 2021. A Purkinje effect should be considered in the statistical works. The possibility that the change of Betelgeuse pulsations forecasted by George et al. There are already evidence in the infrared data of Betelgeuse. And we know that the great minimum of February 2020 was the coincidence of a great dust cloud expelled during the main pulsational minimum, and also in coincidence with the modulating period of almost 6 years. The second minimum is only due to a cloud and is more external with respect to the previous one. Concluding with a quotation of ancient observation, there are myths speaking about the painful shoulder of Betelgeuse. This is reported by Wilkin, J.A. So of 1999 paper. So the ancient people, even 2,000 years ago, already knew that Betelgeuse changed its luminosity intrinsically, not due to the atmospheric extinction or Purkinje effect. And with that, I conclude thanking you for your attention.
Costantino, thank you very much.
You're welcome.
We are looking for questions.
This is the most exoplanet-like universe.
Yes. Well, I think there are no questions from the audience. Thank you very much again, Costantino. I think we are closing now the morning session, session A, and we will be back again at midday at Central European Time. The next session will be moderated by Vereshchagin, and we will start soon in a few minutes to test the presentations. Can I ask to put back the program for next session?